Welcome everyone. My name is Jacob Hess, and I'm here to take you from zero to engineer.
Welcome back everyone, and welcome to the IP version 6 lesson, or the Internet Protocol version 6 lesson. Well, we will learn the what, why, and how of IP version 6. And if you haven't heard of it before, well, we will be becoming very familiar with IP version 6 over the next couple years as we are finally actually implementing this across the globe. So let's go ahead and jump in and look at our agenda. We'll start out by discussing in a nutshell what IP version 6 is and why we are having to even talk about it right now and what's going on with it. And then we'll look at some benefits and improvements of IP version 6 over IP version 4. And then we'll break down the address and look at how we can perform abbreviation to summarize a very long address in a much shorter context. And then we'll look at the different types of IP version 6 addresses and how they are actually assigned. And a lot of this stuff isn't too much different from IP version 4, but there are some really good improvements. And of course, the addressing structure is completely different. So that's the main thing that we're going to take away from this lesson, actually. So let's go ahead and jump in and look at what IP version 6 is. So in a nutshell, it's really just a new addressing structure for the internet, right? For IP, for Internet Protocol. Of course, this affects private networks as well. But the reason why we have IP version 6 is because we needed a larger addressing structure. And it's a 128-bit address, which is represented as 32 hexadecimal digits, whereas IP version 4 was just 32 bits, right? And it was 32 actually ones and zeros, whereas now we have 128 ones and zeros. But these 128 ones and zeros, which will be a really long to write out, are just represented by 32 hexadecimal digits. So the address itself is comprised of 8 groups of 4 hex digits. So here we have one group of 4 hex digits, 2 groups, 3, 4, 5, 6, 7, and 8. So you can see we have a total of 8 groups, and they're separated by colons. This is what a complete IP version 6 address looks like. Now, it's 2 to the 128 IP addresses because it's 128 bits in length, right? Whereas IP version 4 was 2 to the 32, and that provided us with 4.29 billion IP addresses. Now with IP version 6, we have 2 to the 128th power, giving us 340 trillion IP addresses, and that is the number we have written down here. 340 trillion, which is actually a number called undecillion. 340 undecillion IP addresses. And so what that equates to is really a bunch of IP addresses per every square meter of the Earth. It's a lot, 667 sextillion addresses per square meter of the planet. Wow, that's a lot. And we're able to use IPv6. We don't have to use it so sparingly like we had to do with IP version 4, because with IP version 4 we had such a small amount of address space. So you can kind of get the idea. This is what IP version 6 is. It's a bigger address. There's some additional improvements made to the IP protocol stack as well with IP version 6, but the gist of it is the address is completely different, and we now have the ability to have a lot more addresses than we could ever have with IP version 4. Now, another good thing to understand is that IP version 6 is technically on a separate internet than IP version 4. Now, we do have gateways between IP version 4 and IP version 6, and we can do things like tunnel from IP version 4 into IP version 6 as well. But technically, there are websites that are IP version 6 only, and the only way that you can get to them is by going through the IP version 6 internet infrastructure. So technically speaking, they are separate kind of internets, so to speak. Although there's the same hardware. So we have one router that might be running IP version 4 and IP version 6. In fact, a lot of hosts, in fact, pretty much every host now runs both IP version 4 and IP version 6 locally on the machine, so things are supported. But whenever you really think about it, it's kind of like two separate internets. So, all right, that's that point, and you can just keep that in mind. And now we'll discuss the why of IP version 6. So why in the heck do we have IP version 6, and why do we have to learn this new thing? Well, the internet needs room. We do not have enough addresses, and we've really been running out of addresses. So let's take a look actually at this IoT chart. You can see, and you can know that over time, we've just been increasing the amount of devices we have. And we call this the Internet of Things, where everything we can think of is now being connected to the internet. And since about 2000, and let's see when things really took off. Around 2002, 2003, things started really taking off. And this is the projection for 2020, on this chart at least, is 50 billion connected devices. Point is, you can see here that we have all these different devices that are connected to the internet, and we're vastly exceeding the amount that IP version 4 could support, which was 4.29 billion. So this was actually thought about a long time ago, and that's why IP version 6 has been created. So let's discuss that a little bit more now that you have kind of an idea of the high level of why we're doing this. It's because we have so many devices, we need more addresses, right? The internet needs room to grow. And here we have a chart. This chart was created to show you how the address space for IP version 4 has been exhausted over time. And by 2011, we actually exhausted the entire IPv4 address space as the last blocks of IP addresses were handed out in 2011. So let's look at a quick timeline here, but you can kind of see on this chart from the year 2000, it started dramatically just decreasing the amount of available IPv4 addresses to the last one was handed out in 2011. So let's look at a little more history here. Before 1998, we had predicted that the IPv4 address space was going to be exhausted. Now, IPv4 was first created in the late 70s, and that's when we started using it. And so in that time, we didn't realize how many addresses would actually be needed. If there was some more foresight on that, then we would have started out with something a lot larger. But here we are. We're now using IP version 6 and IP version 4 at the same time, and we're migrating to IP version 6. So we did know this was going to happen, right? Pre-1998. So in around 1998, December 1998, we officially created the standard for IP version 6 under RFC 2460. And that can be found on the internet. You can read through that RFC if you wish. And then in 2008, we expected the IP version 6 adoption and transition to be complete. But we weren't anywhere close to that. It was very, very slow. And there was a lot of companies and things that didn't want to take the first step. Nobody wanted to be the first one moving to IP version 6. So we did some things to make sure that we actually started migrating to IP version 6. And really, people started to really become aware of it in 2011 when the IP version 4 address system was officially exhausted. So everybody, I guess, started to think, well, you know what, I guess we should really start focusing on this migration to IP version 6. Now, we have had workarounds. It wasn't like the internet just stopped working because we ran out of addresses in 2011. There's workarounds with IP version 4, and then there's some blocks of addresses that can be reassigned when they become unused, etc. But officially, yes, we did run out of addresses then, and that woke everybody up in 2011. And so in 2012, actually exactly on June 6th, major providers planned on turning on IP version 6, connecting to the internet backbone, and calling that the World IPv6 Launch Day. And these are actually the logos. So this is the logo here on the right for the World IP version 6 Launch Day. And yeah, cool thing. So everyone came together, major providers turned IPv6 on officially on the internet backbone on that day. And since then, the adoption has been increasing quite dramatically. And if you want to do a little more investigation yourself on that, you can actually just go to google.com. Let's see here. We can go to google.com. It's actually just /IPv6. IPv6, yep. So we can go there. You can watch a cool video actually where Vince Cerf, who created IP version 4, he'll give you a nice talk about IP version 6, actually a really cool video. So there's interesting stuff on this article, but the point is we can go to the statistics section here and we can see the current IPv6 adoption according to Google. So IPv6 access to Google servers has been being graphed, and you can see that since around 2011 things really started picking up here on IP version 6 adoption. So that is a nice little reference for you. And here you can also see per country IPv6 adoption. So nice little website, google.com/IPv6. All right, so that should really help you understand why we are now transitioning to IPv6. So let's go ahead and look at some benefits and some improvements that have been made to the IP protocol stack with IP version 6 coming along. So first off, and this is huge, we no longer use this thing called a broadcast There are no broadcast messages. We do not have a broadcast at all. Instead, we've enhanced multicast with IP version 6, and we utilize a better method to multicast. So now we really just have the unicast, a single source to single destination, just like as always, and a multicast, just like as always. But the multicast has been improved. And that's when we're sending from a single source to multiple destinations. And it's now more scalable. And instead of using broadcast messages, IPv6 now uses an enhanced multicast to take care of what it used to do with IP version 4 broadcasts. Now, this does not mean that there is no longer a concept of a broadcast domain. It just means that IP version 6, we don't have the broadcast message for layer 3. There are still layer 2 broadcasts possible. Again, we're just talking about IP version 6 here, the Internet Protocol. So, primarily we have the unicast and the multicast, but there's one other type of message we have, and that's called the anycast. And the reason why we have the anycast is to make the updates from router to router more efficient. So anycast is kind of like a multicast in a way that it's addressed to a group, but the message only gets received by the nearest node in the group, so that routing tables will get updated more expediently. More efficient updating of routing tables from router to router. And that's why we have the anycast. All right, so important thing, we do not use broadcast messages IP version 6, and we have a new messaging type called anycast. And the structure of the address has been improved greatly. It's now much more efficient and hierarchical. So it's created in a way that we can really make it hierarchical and contiguous across the entire globe. Whereas with IP version 4, our routing tables were getting so big because we had all these little chunks of address space positioned all throughout the world in a non-hierarchical fashion. It was hierarchical where it could be. There was some hierarchy, and there still is some hierarchy to the way IP version 4 has been deployed across the planet. But IP version 6 and its much larger address space and hierarchy being kept in mind is allowing us to have a better hierarchy in smaller routing tables on our routers on the internet, making everything much more efficient. So here's just a little map of what a hierarchy looks like so you can kind of get an understanding of what we're talking about. The way that our routers build routing tables is much more hierarchical, so things can be summarized easier from router to router. Like, for example, here's a summary of these networks, summary here, and then this one summarized these. So just like in IP version 4 we talked about supernetting, that's actually accomplished a lot easier in IP version 6 and makes our routing tables better. All right, so that's one way that the addressing structure has improved. But we also made our masks a lot less complicated. And our service providers will generally assign a public IPv6 block as just a /48 mask. Now, /64 is actually the standard and default mask for any host. So if you check out the address on your host computer, it's by default going to have a /64 mask. That's something definitely to remember. Hosts will always have that. Now that makes things a lot easier because no longer are we wondering what the network mask is right away. And we could think that would be difficult to try to figure out with a 128-bit address. And so with the formulation of IPv6, we made things a little bit more easy. The last 64 bits are always for the host. So the mask is always going to be a /64, meaning the first 64 bits is the network prefix. And here we go. We have a IPv6 address kind of broken down where you can see the first 64 bits of the entire address is for the network portion. Now the global routing prefix, this is actually a public IPv6 address, or a global rather, meaning that it's routable on the public internet. There are other types. We'll talk about this a little more in a minute, but here we can see the first 64 bits is for identifying the network information and the subnet information, and then the last 64 bits are all host bits. So literally the entire half of a IPv6 address is designated for host bits. Now you might think this is a lot of possible hosts, and it is, but there's so many addresses available with IPv6 that we don't have to be that conscientious about wasting host addresses. And whenever we're assigned a public subnet from our ISP, it's normally going to be a /48, giving us 16 total bits to manipulate for our subnet and to chop up and use in our organization. We get this whole 16 bits. So there's just a lot more addresses. We can do so much more with it, so much more easily. So hopefully that helps you understand the difference here, and that the last 64 bits are always host bits. And that's why every single IPv6 address that's assigned to a computer is a /64 mask, meaning that it stops here. All right. And then lastly, we have better security. So IPsec, IP security is by default a part of IP version 6, whereas it was added on top of IP version 4. So it was created, IP version 6 was created with better security in mind and also better support for quality of service for our things like phone and video traffic. So if we get a better experience with IP version 6 and it's more secure, then that should make people more happy, right? At least that's the way I'm thinking about it. So these are some ways that we've made IP version 6 better and some of the benefits we get with migrating to it. Now, these are some of the main ones. There are more. I didn't mention them all. And there are more improvements and changes, but these are the main ones. All right. So now that we understand the benefits, let's break down the address structure a little bit more, and let's look at how we can abbreviate the addresses. So we need to understand the address abbreviation rules first. So there's 3 rules to abbreviation. We'll go over them one at a time here. So the first rule is we can drop any leading zeros in the address. So let's bring up an address here. We have a example IPv6 address. So anywhere we see one series of 4 hex digits, which are sometimes called a hextet, whenever we see this, we can actually remove any 0 that's in the front. That's called a leading 0. So if we have, for example, if we had 0003 here, we could remove all the first zeros and it would just be a 3. But in this case, we have 0370, so we can remove this first 0, making it just 370. And over here we have 0db8, and we could just remove this first 0 here, making it just db8. So it would look something like this without any of the leading zeros, right? Make sense? So that's one of the first things we can do to shorten our addresses. Now, if it's all zeros, that's not necessarily considered a leading 0, but we are going to be able to do things with these as well. So just hold your horses if you've noticed that those are there. So drop leading zeros, that's the first thing. Second thing is, when we have a group of 4 zeros, we can replace that group of 4 zeros with a single 0. So let's look at an example. And we see here a group of 4 zeros. When we have a group of 4 zeros, we can replace it with a single 0, just like so. So we've taken those 4 zeros, and now we've rewritten the address with just a single 0 in place. All right. Now the next one actually saves a lot of room when we have a lot of zeros, and that is that when we have contiguous groups of zeros, they can all be replaced with a double colon. But you can only do it one time in the address. Here's an example. If we have 2 contiguous or adjacent groups of all zeros, we can replace all of them with a double colon. Now, it's 2 or more, actually. So it could be these 2. If we had another group of zeros here, we could summarize all 3 with a double colon. Or you get the point, right? It's from 2 or more, double colon. And let's look at what that looks like. Here we go. It's literally just a double colon. So all those zeros and the colon gets replaced by a double colon. So those are ways that we can abbreviate our address, making it shorter. So now you see we ended up with this address rather than this long address up here at the top. Now you may be thinking, well, it doesn't look that much shorter, but I used this address to explain this to you. However, in reality, there's going to be usually a lot more places that will have a series of zeros and we can abbreviate more. And I'm about to show you a very good example where we have an address that is comprised of pretty much all zeros. So let's check that one out. That's going to be the loopback for IP version 6. So the IP version 6 loopback looks like this. All zeros ending in a 1. So we can go ahead and use all those abbreviation rules that we just talked about on the loopback address as well. But I want to show you something, and I'm going to go ahead and just pull up my command prompt so you can see here that it really is a loopback. Now, with IP version 4, remember we had 127.0.0.1. That was a loopback. We ping ourselves when we ping that. Now here, we can ping all the series of zeros, and it's a loopback as well. So 000, let's see, typing all these out. I think this is it, 0001. All right. Now, you can see that it's went ahead and summarized it. So how in the heck did it summarize it to this? It took all this that we put in and automatically was like, hey, we can just summarize this down. So let's look at how we get there into just having a : 1. So we could ping : 1, and that's a loopback. I'm pinging my own network interface card. So you get the point. How do we summarize this loopback address down to just : 1? Well, let's run through our rules, and Our rules are drop leading zeros, turn 4 zeros into single zeros, and then also replace 2 or more contiguous zeros with the colon. So if we take this IP version 6 address and we drop all the leading zeros, what does that give us? Well, we're just going to be dropping these zeros here, right? All these are not leading because they're groups. So we drop just the leading zeros, and then we have just at the end the :1. Then we can take 4 zeros, groups of 4 zeros, and turn them into single zeros. So the next step would look something like that, right? And then if we had 2 or more contiguous strings, we could then just do this, : :1. Now we don't have to go through each individual step. We can just drop leading zeros and then say, oh, we can replace 2 or more contiguous strings. Here we have all these contiguous strings. We can replace all that with 2 colons, and we replace the last one with just the 1, right? Because we get rid of the leading zeros there, giving us just : :1. So that's how we get the wonderful IPv6 loopback address of : :1, which is only a single address, and whereas in IP version 4 we had a whole entire class A range for loopback, which was crazy. But now in IP version 6 it's just a single address for loopback. All right, so that's our address abbreviation. Now we need to understand some more stuff about some specific types of IPv6 addresses. This is going to actually wrap it up for us on our main IPv6 lesson here. So these are the different types of addresses. We have a global address, we can have a link local address, and we can have a unique local address. So we'll talk about those 3, and then we'll talk about how to actually assign host addresses. So what is this global address thing? Well, we looked at something already that had a global prefix and a subnet, and then we had our host portion. This never changes. The host portion is always 64 bits. But the thing about a global address, it's a unicast address with a globally routable prefix. And that's why it says global prefix here, because it means it's actually routable on the internet. The global address is an IPv6 address that is routable on the internet. That's the main thing to know about it. It's used for talking out to the public internet, and it starts with a range in the 2000s. Now, the 2001 with a /16 mask is what is being assigned from IANA to the global internet registries who hand out these IP spaces to the different internet service providers. So they're handing out these, so a global address will always start with 2001 for the time being. So anytime you see 2001, you know that's a globally routable IPv6 address called a global address. Now, there are these 3 different types of addresses, and it is possible for a single network interface card to have all 3 types of addresses assigned to it all at the same time. And we're going to have to get used to that. This is completely unlike IP version 4, whereas in IP version 4, you only ever had 1 address assigned to any one interface. IP version 6, you can have multiple, and you will have multiple addresses assigned to the interface. All right, so that's the global address, guys. Next one is link local. And this is only for connectivity on the local network, and this is assigned by default. Every NIC has one of these, a link local address. We will always have a link local address. Again, we will always have a link local address, and it's automatically generated on the interface. So your computer already has one of these, every router already has one, and they start with FE80. Now, these are not routable on the internet, but I can bring up my command prompt again here, and we can take a look at it by just typing ipconfig. I'll do a /all here, and I'll scroll up to my wireless adapter, and I don't really have IPv6 completely set up, so I don't have the global address, but you can see I do have a link local IPv6 address, and you can see it does start with FE80. And then it has a unique identifier in the last 64 bits of the address. So the whole first 64 is just FE80 actually, right? So if we wanted to break this down like we did the global address, we could just look at it like this. It's really just a series of host bits, and in the beginning, in the first 10 bits, it's FE80. Now it doesn't mean this whole thing is a /10, we're just saying /10 here because that's the first 10 bits that create FE80 : right? All right, so that is the link local. And again, every single interface has that. So I'm looking at my wireless LAN adapter. It has one. Let's see. By default, my VMware adapter has one. See, FE80. All my adapters, if they have IPv6 enabled, they will automatically have this, guys. No matter what, you're going to have the link local. It will always be there. It will be there alongside your other IPv6 addresses. So the next type of address we have is the unique local address, and it always starts with FC00. And this is more like the private IP addressing of IP version 4, and it's for organizations to use privately. It's also not routable on the internet, just like the link local address. It's akin to the private IPv4 addressing space. So again, we can have each one of these on our machine all at the same time. Global address, we need that if we want to be able to get to the internet, but we'll always have at least these two. If we can get to the internet, we'll always have at least a link local and a global. But if we also want to have some private type of addressing for our organization, that's a separate type of address called the unique local address. And our machines can literally have all three of these at once. All right, so those are different types of addresses. Now, how in the heck did the addresses get assigned to hosts? Well, it's very similar to IPv4. First, we can just manually configure it. We can go into our network interface card, make sure IPv6 is turned on, and manually put in an IPv6 address. We can manually configure any of these global, link local, or unique addresses on our machines or our routers. So manually configured is one way, and then we have auto configuration. Now, auto configuration is huge in IPv6. And again, the link local address is always automatically configured. Now, automatic configuration can happen in two different ways. One is it's just going to auto-generate the host portion. So the last 64 bits, it'll automatically generate a random address with the host portion. The other way this happens is using something called the Extended Unique Identifier 64 format. And what that does is it looks at the MAC address of the machine. So in that case, it'll look at the MAC address of the network interface card. It will split it in half. So it literally takes the 48 bits, splits it into two 24-bit chunks, and then shoves a 16-bit chunk in between it, in the middle, which makes it a 64-bit host address. Make sense? 48 plus 16 equals 64. So then it holds that entire space. It takes that entire space up of the host field. That is EIU or EUI 64. So those are the two ways that our host portion of our address can be automatically configured. And then what's another way that we can get addresses? I know you guys have probably been thinking of this. Do we have DHCP with IP version 6? And yes, we do. It's called DHCP version 6. And this is only used with our global address types and our unique local address types. We would set up a DHCP server, such as on our router or such, and then it can hand out a dynamic address based on its global network ID, or a unique local address based on its private unique local network ID. And it uses something, or your host uses something called the DUID, the DHCP version 6 unique identifier, to get an IP address from the DHCP v6 server. So it uses this thing called the DUID, guys, whenever it's requesting a DHCP v6 address from the DHCP v6 server. And just a few more important things we need to note about addresses. First off is that every single computer will always have the link local. Again, every computer will have this link local address. Also, every computer will have multiple IPv6 addresses. We just need to get used to that. We'll either have a link local and a global, or a link local and a unique, or maybe all three of those. And you may have been wondering, if we have these three different addresses, who's the default gateway for our network? Well, the default gateway is going to be the link local IPv6 address of the gateway router. The link local IPv6 address. That's how we do that with IP version 6. We use the link local thing. So if you're on a local network and you have a link local IP that's automatically generated, your router will be able to talk with you, your default gateway will be able to talk with you on that same link local network that is automatically created. Pretty neat, huh? So that is our IPv6 address types, and that actually wraps up this lesson. So we can go ahead and do a recap. So first off, it's good to note that IPv6 addresses are 128 bits in total length. And we need to make sure we understand the different ways to abbreviate the IPv6 address. Understand that the loopback is : 1, right? It's just a single address for our loopback in IPv6. We need to know that the link local addresses always start with FE80. Remember that? Every single network interface card will have something like that that starts with FE80. And we also need to know that the first 64 bits, which is the first half of our IPv6 address, is the network portion and the routing portion, and the last 64 bits is always for the host. And our address masks are always /64 for our hosts. So If we look at a network ID, it might be a /48 or a /56 or something like that. But when we actually look at our host global address or unique local address, it's always going to be a 64-bit mask, /64. And automatic addresses can be based on two different types of things. They can be either randomly generated, that's one way, or based on the MAC address, which was the EUI 64. Remember that one. We can also assign our addresses either automatically, which we talked about two ways to do that, or we can manually configure them right on the card, right on the network interface card on our router or on our host machine. I know this is a lot of points on our recap, guys, but these are all important things to know about IPv6. Nice, real summarized lesson here. And to get on the internet, remember, we need to make sure we have a global IPv6 address, but we'll actually need two addresses to get on the internet. We'll need the global and we'll need the link local. So 2 IPv6 addresses in order to have internet access. And the world is still transitioning to IPv6. And we're going to continue to have both IPv4 and IPv6 running side by side. I'm not sure how long it's going to take to go complete at IPv version 6, but over the next couple years, there is going to be major headway made, and I would suppose by 2020 we'll have most of the world migrated, at least on the public internet. Most of the world probably migrated to IP version 6, but that's just kind of a prediction. I don't really know how fast it's going to happen, but it looks like things have been picking up a lot, and we will see a large and faster rate of adoption of IPv6. Now, we may still have a lot of networks that are running IPv4 internally and privately and don't transition their internal networks to IPv6. So the full transition to IPv6, who knows how long that's going to take. But again, we're going to continue to have both IPv4 and IPv6 running side by side for quite some time. And that is the IPv6 lesson. I hope you learned a lot about IPv6, and we did summarize a lot of things here, and now you should have a great understanding of what it is and why we're moving to it. Thank you very much for viewing, and I'll see you in the next video.
Jacob Hess here. Thank you guys for viewing the video. I hope you really enjoyed it. And I'd also like to remind you that if you're truly serious about your career in information technology, be sure to check out our Career Blueprint and Engineer Training Program at www.zerotoengineer.com.